The demonstration in question involves placing a camera at the end of a table and then moving an object along the table away from the camera, and it disappears bottom first. But then when they zoom the camera in, the object comes back into view.
I'll only be concerned with Flat Out Truth's video here, because that is the only one I presented, and that is all that will be needed to establish the truth of the matter. Once again, Dave has either confused, ignored, or misrepresented. It's become increasingly obvious that he will only continue down this path, as admitting such a defeat to such a flat earth truth would not look very good for his debunking business and reputation. Objects disappearing bottom first is supposed to be a bedrock foundation for the globe after all. I almost ignored his video, knowing he will never actually debunk this topic and only provide the usual strawman arguments, but revealing all the sly tactics and misdirections in this case is not only educational, it's important.
Now, the first thing with this demonstration is the obvious question. Are we certain that the camera is correctly aligned with the table? Is it looking just across the surface, as should be the case for a flat Earth representation, or is the camera actually slightly below the table? It's hard to tell from Flat Out Truth's video though, because he doesn't raise the camera up to show us.
If the center of the aperture was under the table, he would not have been able to zoom back in on it. You can't zoom through a physical object. It did not disappear due to a slight focus blur along the edge either, as we will see. Anybody else that does this small-scale test wrong, flat earther or not, is irrelative. There is a reason why I only share some things and not others. This all goes back to what Life is Short already explained to you, Dave. The shortening of your horizon vanishing point and the compression of visual information beyond it, which occurs millimeters, feet, or miles off a flat surface, as we have seen with the light over the lake and with the moon at high altitude. I think it's time for a quick brush up on this.
So again, keep in mind that if this is, let's say it's 10 to 15 feet away, and the distance between myself and the debris on the other side is 410 feet, that I am cramming 400 feet of information between the red tip of that arrow and the purple horizon line, which is a lot of information. And so what ends up happening is that your horizon shortens along the lower field, and whatever is there disappears into the essentially a gap that's formed. But each halving of a frame puts twice the amount of information in the next halving. So you can look at the 50% numbers on the side. You can look at the amount of information that I'm cramming into each subsection. And again, the proof of this you can find when I analyze the hallway footage. And you find that in, again, the lower 1/4 of the image, I have 9 feet, and then it goes 18 feet, 36 feet, 72 feet, and it doubles each time. And by the time you get to the arrow point, it's only about a half mile, which means that if I'm a 6-foot observer and I see 3 miles, then I'm cramming 2.5 miles between the very top black line and the purple line horizon, which is quite a lot of information to be crammed in such a small space. So I'm not going to go through this in too much detail. I want this to be short. Just remember that as you lower your eye height, you're cramming more and more information into a smaller space and it gets lost. So, but it remains 50% of your vision. So the floor is still 50% even though you're not seeing as far along the floor. So what happens to that information in the distance? It disappears essentially into this, what I'll term, I guess, a horizon gap. And again, more information on this you can find on my channel or with the discussion with Jeranism. Same thing here. Again, at different heights you can see how I'm compressing different information. So when I'm 8 foot tall, the ceiling is getting compressed, and as I get down to 1 foot tall or 0 feet, or essentially half a centimeter off, the floor is getting compressed. And this is just an aspect of how our vision works. It has nothing to do with curvature. So same thing again, I'm in here in a Walmart and then no light is visible. I'm along the floor. So there's no reason to believe why this aspect of vision would change if I were to remove the walls and the ceiling of this Walmart and extend this floor for miles and miles, and I were just to stand up, it would be the same exact phenomenon, but just occur further and further away. There's no reason to believe that this is curvature. So I just want you to focus on that. It may not be that the bottom of the objects disappear from being too small to see, but rather that the ground can only extend so far when we are close to it. We can only see so far along the ground. It's not so much the object itself or the bottom of the boat itself getting too small. It's the fact that you can't see that far along the ground, but it still occupies 50% of your vision. So using the loss to calculate theta for this camera within these conditions, I can now calculate the amount of loss over any distance. Alternatively, I can calculate the amount that is resolved with a change in height, just like we did before. So plugging in at 260 feet, I would expect a loss of about 1 inch. At 380 feet, I would expect a loss of 1.43 inches, and so on. If theta is held constant across any similar triangle, we can restate our formula as h1 over h2 equals d1 over d2, right? And as those ratios then could correspond to one another across tangent theta, as h1 over d1 equal to h2 over d2.
Depth of field refers to the areas of the image in front or behind of the subject that you're focusing on.
Basically the areas which are out of focus. So if you see a portrait, for example, with the background very blurred, this is referred to as having a shallow depth of field. Whereas images like landscape photos, where everything is clear from very close to far away, is said to have a deep depth of field. I find it easier to think of it as depth of focus, and it's affected by 3 factors: focal length, aperture ratio, and subject distance. Although the focal length and aperture ratio are kind of linked. If you were to take lines from either side of the lens's iris opening and have them cross each other on the subject, that is the point where the lens is focusing on and thus is perfectly in focus. As those lines get further apart, things get more out of focus.
The issue isn't over focus with Flat Out Truth's test, as we will see, but an important factor to note here is that Dave himself has just presented another argument as to why obscuring bottom first can occur on a flat Earth. Camera focus. Thanks, Dave. So we have visual compression, mirages, downward refraction, haze, uneven surfaces, foreground objects, magnification, and now focus blur. I guess 8 reasons aren't enough for a flat Earth? Well, 7 if you include haze with foreground objects. No, only Earth curve that never geometrically lines up and always needs selective miracle-working refraction? Crazy.
If you physically open the iris up, then the lines are starting further apart from each other and thus will move away from each other quicker, so things will drop out of focus faster than if we had the aperture closed down. When we zoom in, we're actually magnifying the appearance of the iris across the front of the lens, and so again the lines will be starting further apart, and so things will fall out of focus sooner, whereas zooming out to a shorter focal length creates a deeper depth of field. And last but not least is distance. With the camera right up to the edge of the table, the difference in distances between the camera to either end of the table is huge.
Kind of like it would be at 6 feet above a flat surface that goes on for thousands of miles. Huh.
So if we focus on the closest end of the table, the far end of it goes out of focus. If we focus on the far end, then the near end goes out of focus. Now, I recreated the setup along this countertop behind me, but I did it in a more controlled manner. The camera I used was my Sony a7 IV with a Tamron 28 to 75mm lens, because on this lens there's a little white marker which is used as a guide to align where the lens mounts to the camera, but when the lens is locked in place, it sits exactly in the middle of the lens mount, meaning it's running across the middle of the sensor.
Where is the proof that some alignment mark is aligned with the internal sensor? Why are you worried about aligning the sensor? You need to worry about aligning your aperture, since that is where light first enters into your camera.
So I placed the spirit level onto the camera to ensure that the camera was sitting level.
This is a Nikon D7200 with 18 to 140. So I'm going to show you that even though you see here that it is level on top of the camera, on live view you can actually see that it is also level. But since it's placed on top of the camera, we cannot see for sure if it is tilted up or down. So I'm going to place this very simple level on top of the lens, and now you can clearly see that the camera is tilted down. Okay, so the best way to establish that if indeed you're looking straight is to place this type of level, which is a very simple level, on top of the lens. Okay.
And when I lifted the camera so that the marker on the lens was meeting the bottom of the level, I knew the surface of the counter is sitting exactly halfway up the camera lens.
Sure, it looks close in that view, But let's see where you either go wrong or simply and purposely strawman this entire demonstration.
And when I place an object in front of the camera and then move it back, the bottom does not go out of view.
I am very, very sneaky, sir.
I see that.
Sneaky, sneaky, sir.
The entire premise is to go beyond your horizon/vanishing point. You did not move your object far enough, and you're also using a shorter surface. This was designed to fail, just like your previous attempts. You can see where the camera's horizon is and how much surface area you can see from this perspective. When the object is at its furthest distance, we still see the horizon and more table beyond it. The loss of visual information across an actual flat surface does not occur until an object moves past or into your visual horizon. If the edge of your table comes first, then you either need more table or a lower and more even vantage point, or perhaps a much smaller camera with a smaller lens.
I can only reproduce the flat Earth as results of disappearing bottom first when I lower the camera down slightly.
Really? So why don't you zoom back in on it after you lower your aperture below the table? Why don't you use more surface area? Why don't you place the object beyond your horizon where your perspective lines converge? Why don't you correct people when they ignorantly say a flat Earth wouldn't have a horizon? Is it because it destroys all your attempts at misdirection?
Which obviously isn't possible on a flat Earth unless you're standing in a ditch.
Well, the world needs ditch diggers too.
Nice try.
Tell me, Dave, was Life is Short standing in a ditch when he held his camera above a calm and flat pond? Have you forgotten this too? Let's refresh your memory.
That actually ties in nicely to DST's next examples, which come from Life is Short. This involves a few different clips, two looking over a lake, one during the day and one at night, looking at a light across the lake, and showing that if the camera is placed near the water, then objects can disappear from view. The one in the day doesn't make particularly clear what the object is that we're looking at, but I think it's a fair assumption to say that it is something floating at the water's edge across the lake, so it's right next to sea level.
Everything you said will be addressed, Dave, but I must point out the elephant in the room to everybody first. Regardless of the excuses, we are watching objects vanish on a flat surface, whether locally flat under the globe model or all flat. That is what we are seeing, whether it's due to refraction, mirages, compressed visual angles, waves, grass, uneven ground, etc. Objects will vanish bottom first on a flat Earth. It's inevitable. For the entire globe community to deny this still demonstrates the extreme levels of cognitive dissonance and mental gymnastics that is occurring with people who are still resisting the truth of our reality.
The nighttime clip is using a light that has been set up 2.5 inches above the waterline. Life is Short then lowers his phone camera down and states that as his phone case touches the water, the light disappears.
And there, I'm just barely touching the ground, touching the water. You can see the ripples just starting as the iPhone case just touches the water.
And then states that that means the observer height when the light disappears is about 1/2 inch above the water. So when that happens, the observer is lower than the light source. The light source must therefore be travelling downwards into slightly denser air, and so refracting.
That is only assuming there was a significant enough of a change in the density of the air, within that 2 inches of gap, across about 400 feet of water. On a nice, calm evening, that very small slice and stretch of air would be highly uniform in temperature. According to Wikipedia, there is only a 1% change in atmospheric refraction for every 3 degrees Celsius.
There was no refraction. You could not really say that this wasn't a refraction phenomenon if you were to go back and look here at these conditions. This is across 400 feet. It's crystal clear. The water is not moving whatsoever. and the temperature is roughly the same between the water and the outside air. It was a fairly warm night, so
Okay.
I'm not too concerned that refraction would play almost any role in this whatsoever.
The bottom line is that you have no good reason to claim refraction would cause all of the light to miss the camera. The most you would expect in that small slice of stable air is some shimmering of the light, and we don't even see that. It's a stable light source.
Here it is zoomed in a still shot. Missing now. And so some still shots again. As I'm about 1.5 feet off the water, you can still clearly see the light, and you can see a little bit of reflection on the water with the light, but the light is still visible. And then as I am 0.5 inches off, there is clearly no light visible whatsoever. And then in the bottom of I just took some still shots of how that, when it was auto-focusing, and you could see the halo, and how that halo definitely appears to be cut off bottom first.
Do you care to explain that to Dave? Tell me how refraction cut off an auto-focusing halo of light, clean in half. Do you have proof and demonstrations of this? Demonstrate this without a surface involved to compress your angles and just by using refraction. You cannot. This is even more proof that it is the sudden loss of visual information due to compressing visual angles and shortening of the horizon. The parts of perspective that nobody has taught you about. Earth curvature has nothing to do with it, nor is it present in the dozens of examples that has been shown before.
So what should we be seeing if we were to be living on a globe? If this phenomenon right here is because this water is curved, and curved water is what obstructs our vision of things beyond a horizon, a physical horizon, then what should we be seeing? Well, the short answer is that we should be seeing this entire light. There should be no loss. And so the drop essentially should be about 0.004 feet, or about 0.048 inches, or which comes out to about 1.22 millimeters. And if you know how big a millimeter is, that's extremely small. And we are definitely far more than 1.22 millimeters with that light above the water. Furthermore, my horizon distance should be about 1,314 feet, which is well beyond the 400 feet that we were at. So by all accounts, we should be seeing this entire light the whole time.
Another clue that this demonstration from flat earthers is flawed is that their objects begin disappearing as soon as they move them away from the camera, which is not what we see in reality.
Of course they do, Dave, because the horizon is very close to you, with such a compressed viewing angle. Once again, the higher you are, the further your horizon will be. It obviously doesn't need to be a globe for this to occur. It's the easiest thing to demonstrate, and it's very strange that some people are still denying this. I don't know what you mean by in reality when that is a real countertop and a real camera. This is some really desperate hogwash you're giving us, Dave.
In reality, they appear to rise up first, and
What we see of the lid is above the camera's eye level, thus it will appear to converge down due to a very close horizon. And yes, this is reality, Dave. Try to learn it.
then start becoming obstructed whilst dropping down, which we can produce perfectly on a table, as long as the table has a curved top to it.
And as we have seen throughout all my videos, it doesn't have to be curved, Dave. It can be perfectly flat, with or without refraction. Ironically, you are showing what a flat Earth is like in reality, though. It's very, very common to have uneven ground, hills, swells and waves, etc. Once again, a ball isn't not required to have bottom-first obstruction or loss of visual information. There is no way out of this, Dave. You can endlessly strawman this back and forth with the same old tactics, but the fact will always remain. Objects can and must eventually vanish bottom first on a flat Earth. Perspective and atmospheric effects demands it.
However, you might be thinking, hold on, If the camera is lower than the top of the table, then why did zooming in bring the object back into view?
Notice how he never once demonstrates zooming while under the table himself.
Sneaky, sneaky, sir.
Shouldn't it just have zoomed into the edge of the table? And this is where things get pretty cool in my opinion.
I fear you're underestimating the sneakiness, sir.
When I first saw this demonstration being done, one thing I immediately noticed is that when the object in question is getting moved back, the camera focus does not move with it. If the camera focus was set to follow the object, then as it moves back, the camera would shift to track it, or at least track the person's hand. This would cause the near edge of the table to move out of focus, but it doesn't. The camera's focus is staying fixed on the edge of the table, and the object is moving out of focus.
As was mentioned, using that excuse just adds to the list of reasons how objects can become obscured bottom first on a flat surface. Even so, in Flat Out Truth's footage, we can see right through the focus blur. It is highly transparent in his footage. We also see it go beyond the camera's horizon, unlike in your example, Dave. This is why the lid is vanishing bottom first, due to the visual compression and loss of information beyond your horizon or vanishing point. Zooming in decompresses the visual angles, thus you can now resolve it.
But as you can see here, if you zoom in with the camera, you're going to find that it pops right back into view.
Here we can see the lid just begin to come into view, and we can clearly see right through the focus blur. You can clearly see the line of blurring just below the red line, and it is not obstructing anything, but is transparent.
In the footage at the moment, the camera is set to f22, which is the smallest iris opening this lens will allow, and the bottom of the object is clearly obscured by the countertop.
It's really quite simple, Dave. Your blur there, not countertop, is not as transparent, so it is obscuring the bottom.
However, without zooming in, if I just open the iris up from f22 up to f2.8, the iris is now much bigger and part of it can see over the top of the counter, and the bottom of the object now comes into view.
If you could do this at higher camera heights, but longer distances, it would be the same thing, Dave. Also, I would like to point out that not all cameras' iris and aperture changes with zoom. Some remain constant and can rather be changed at any time. None of this matters, though. The compression and loss of visual information beyond your horizon or vanishing point still occurs, whether it's with a camera or a human eye. Whether on a perfectly flat table or pond, high or low, and once again, it's only one reason of many. Give it up.
As long as part of the lens has line of sight to the object, the obstructions can be blurred out of view.
And as we've seen, that was not the case for Flat Out Truth's video, but thanks again for providing another reason for bottom first obscuring on a flat Earth. Much appreciated, Dave.
But as you can see here, if you zoom in with the camera, you're going to find that it pops right back into view.
Missing now. And you can see the halo and how that halo definitely appears to be cut off bottom first.
Because at the end of the day, I can see how those demonstrations could lead people to believe that objects would disappear from view bottom first over a flat surface.
You don't say!
And we're all human, so, everyone gets stuff wrong from time to time. I don't think there should be any shame in getting things wrong. I see it as an opportunity to learn from it and learn something new. And this actually links us perfectly to the bonus debunk.
Here's my bonus debunk. By the way, if Leo gave you 100 space bloopers and only got one wrong, does that negate the other 99? Not at all, Dave.
We have the European Space Agency flying above a model of Earth in the ISS space station. And it's a night scene. Well, night scenes, we kind of expect stars, and wouldn't you know, we have stars above here. But we also have what appears to be stars below here. How can that be? Well, no, they can't be stars. These must be the lights of individual people home, getting ready for work the next day, doing their homework, washing dishes, whatever. But as you'll notice, these pinpoints of light here are the same brightness as the ones back here. So whoever's back here, they must have very powerful bulbs in their lamps at home to match these less powerful bulbs here. Or something else happened, like the European Space Agency screwed up and put the star layer in front of Earth. And let me show you what happened. And this is how it works. Each one of these channels I'm clicking on, these are called channels, but we'll just call them layers, like Photoshop. Each one of these layers can have a file or a video file on it. For example, on my first layer, I have a black background. On my second layer, I put stars in that I made in Photoshop. Pretty neat, huh? And on my third layer, I put a model of Earth. So we have a black background, we have our stars, and we have our Earth. Much like we have here from the European Space Agency aboard the ISS space station. What happened was somebody switched the stars, these are the stars, the middle layer, Earth. Somebody switched the stars and the Earth around on the layers when they were faking this. And so now we have stars in front of the Earth. And I'm going to try to show you this a little bit better. Let me see here. I hope Sony Vegas has like a curves editor like Photoshop. Okay, apparently Sony Vegas does have a curve editor. I have it right here. This top range should affect highlights. The blue, yep, sure does. Okay. All right. And so I probably want lower mid-range. All right, so I want you to watch this. We have stars up here and we have stars here. And I want you to watch that these stars are in fact layered in front of the Earth. And so they screwed up. They put the stars in front of the Earth, not behind the Earth. Why? Because this is all fake. They're faking space, people. We cannot orbit Earth. And with billboards in Oklahoma, I heard, in Philadelphia, and more billboards coming, more and more people are going to be aware, and pretty soon there's going to be a mass rush to throw away their globe Earths in the trash. And there will probably be an epidemic because the landfills will be filled up with nothing but broken, spinning balls. But it's a price we have to pay. And after you throw your globe away, I know it's going to be hard, but you'll get over it. Just wipe the tears away and move on like a good soldier. The rest of us had to. We couldn't believe it either, but there you have it. This is Mike. I appreciate you watching. Please like, subscribe, share with others. God bless.
But as you can see here, if you zoom in with the camera, you're going to find that it pops right back into view.
And you can see the halo and how that halo definitely appears to be cut off bottom first.
Well, that's going to be a wrap. If